Hello and welcome to part 2 of your lesson today. I know the notes are a bit long, but we're just learning how we do use our first derivative, second derivatives, and sign diagrams, and use that information to, like I said, build up to curve sketching. So I know it feels a bit long, but there's really nothing too new in terms of the math. We're just learning some new language and definitions and learning how to put all these things together. Okay, so for part 1 of this lesson, we learned about how we can use the first derivative, make its sign diagram, and from the sign diagram of the first derivative, we can get the min-max values. So then the second part of this lesson, we're going to look at the second derivative. The second derivative gives us information like concavity and inflection points. Those would be new terms that we've never looked at before. So first, we'll just define what we mean by concavity and inflection points. Second derivative, you already know how to do. Sign diagram, you already know how to do. And then when we do that one example at the end, you'll just see how it all fits together. So it shouldn't be that bad. So we have some new language, concave up, concave down. Those look like parabolas we drew back in grade 11 pre-cal, right? And we just would have said parabola opened up, parabola opened down. But now it's not just a parabola, right? We're looking at continuous graphs. And we know that sometimes there'll be more than one min, more than one max. So remember we did some polynomial functions, they just kind of curve up and down. So we're looking at min, max. So any part in the graph where you see a shape like that, this would be called concave up. Anytime you see a curve like this in the graph, that would be called concave down. So I think visually you can understand those definitions. If we look at definitions in terms of how we define it in calculus, we would say if it's concave up, that means it's above its tangent lines. So I didn't draw the tangent lines. We've been doing tangent lines on curves. We've done that a few times. We did it in chemistry. I think you've done it in physics. So if we drew tangent lines, I'll do the best I can. Tangent lines, there, those are the tangent lines. You'll notice that anytime I draw a tangent line, the curve is above it. So that's how we define it in calculus. Concave up means it will always be above its tangent lines. Now, if we look at the slope of these lines, I didn't do a very good job, right? If we look about, I'll go back to grade 10 pre-cal when we learned about slopes of lines, you can see that every time I draw a line, the slope of the lines are increasing from the left to the right. So because the tangent lines are increasing in slope, we'd say that the first derivative would show that that is increasing. So just different ways to define it. So then if we look at concave down, again, visually, we can make sense that it's going down. But the proper definition, concave down, means it would be below its tangent lines. So if I drew some tangent lines as best as I could, no matter where I draw the tangent lines to the curve, our curve is always beneath it. So that's called concave down. Again, look at this series of lines that I drew. The slope of the lines here would be decreasing, right? This would be positive, positive, now it's negative. So the slopes are decreasing. So if the tangent lines are decreasing in slope, that's also another way we define concave down. Or we can say the first derivative is decreasing. So that's your new language today about concave up, concave down. The next slide, we'll look at something called an inflection point. Again, this is a brand new term. We've never used that before, but it's pretty easy. An inflection point is just where concavity changes. So if it goes from concave up to concave down, that means you'd have an inflection point in between where the concavity changes. Also, it'd be the same if it went from concave down to concave up, then you'd have an inflection point in between those as well. So I just drew a partial graph here. So you can see that this would have a change in concavity. The point in the middle where it changes would be the inflection point. So here, I know it's not the full graph, but this would be concave up. And then here, it's starting to go concave down. So right here is where the concavity changes, so this would be the inflection point. We use the second derivative to get concavity. We use the first derivative to get min-max values. We use the second derivative to get concavity. So this portion here, where it's concave up, the second derivative would be positive. And here, where it's going concave down, the second derivative is negative. So you use second derivative to get concavity, first derivative to get min-max values. So if we keep going with our definition, how do we find concavity and inflection points? It's really quite simple. It'll look very similar to part 1 of this lesson, how we use first derivative test or first derivatives to get min-max. To get concavity, we use the second derivative. So step 1, get the second derivative, which is really easy for you guys at this point. Then you make a sign diagram from the second derivative, really easy for you guys at this point. Now, how do you interpret the information from the sign diagram? It's very simple. Any region in your sign diagram that's positive would show where the graph is concave up. Any part of your sign diagram where the second derivative is negative, that would be concave down. Well, what about where it's equal to 0? Well, that would be your inflection points, and we'll get to that on the next slide. So the inflection points would be the point where the sign changes. That's where you get inflection points. Quite simple. So again, this is just a generic example. I didn't put any numbers on there. This is just kind of a pretend sine diagram that I've made. You can tell this region, and we'll just pretend that this is the sine diagram for second derivative of some functions. I didn't actually put numbers. So if this was the sine diagram to match the second derivative, this region of the graph would be concave up because it's positive. This region of the graph would be concave down. This region of the graph would be concave down. And this region of the graph would be concave up. Pretty straightforward. Positives give you concave up, negatives give you concave down. Now, how many inflection points are there? Well, we look. This would be an inflection point right here. It goes from concave up to concave down, so whatever that value is, that would be an inflection point. Now, would this be an inflection point? No, because it's concave down, concave down. So even though there's a point in there, the concavity did not change, so that would not be an inflection point. Then we look at this region, it goes from concave down to concave up, so whatever value that is, that would give us an inflection point. So you only have inflection points when and where the concavity changes. Just a note, just like we did in part 1 of this lesson about critical numbers, same thing for our inflection points. Remember, your f of a has to be defined for it to be an inflection point. And where do we get our possibilities for inflection points? We'd say any possibilities would be where the second derivative is equal to 0 or undefined. Okay, so we're ready to do one example. This one example will review first derivative, second derivative, min, max, concavity, inflection points. So the good news is, if it feels like we're doing the same thing over and over again, we are. And we're connecting the pieces so that next week, we don't have to take any notes at all next week. You're just gonna get a question, say, here's the graph, sketch it without technology. We're gonna use all the information we've taken so far in calculus to do curve sketching from beginning to end. So yes, it's good, it just really builds upon each other. We're reviewing every day, so when we get to curve sketching next week, the questions will be long and tedious, but it shouldn't be that hard. Okay, step number 1, where do we start? And again, remember today we're not actually sketching, we're just learning the steps. So next week we'll be able to sketch them. But today we're gonna learn the math, the procedure, and not actually sketching yet. So step 1 is we get the first derivative. So you take your function, I've already done that on the board. The first derivative of our function is 4x cubed minus 12x squared. Then we need to get our critical numbers from that. So we realize we can factor out a 4x squared. So then we should have 4x squared, x minus 3. Then we make our sine diagram. So we have 2 critical numbers there. We have 0 and we have 3 as our critical numbers. And then making our sine diagram, when you stick a large x value, anything larger than our largest key point, you could use 4, but a million's more fun. So if we put a million through, that makes this region positive. First key point we hit is 3. This is an odd exponent, so it changes. The next key point we hit is 0. That's an even exponent, so the sign stays the same. So this is the sine diagram for our first derivative. Now, what information do we get from our first derivative? That's where we get our min or max values. So let's just analyze it first. What do these regions mean? The negative regions mean where it's decreasing. So this graph would be decreasing from minus infinity to 0 or from 0 to 3. Where would this graph be increasing? Well, wherever we see a positive number, so the graph would be increasing from 3 to infinity. So that's where we get where the graph is increasing, decreasing. Then we look, are there any min or max values? Well, we look, it goes negative, negative, positive. There's a sign change here. So if you did, if we were listening to the first part of this lesson, that means that we have a min value there. There's no max for this graph, there's just a min value. So we know that we have a min value where x equals 3, and there's no max value. Now I'm running short of space, I'm going to try and put it in at the bottom. So we know we have a min value when x equals 3. So how do we solve? Remember that you don't use the first derivative, you'll go back to the original function. So I know it's getting a bit low. Yeah, I think you can still see on the video, I can still see it. So if I replace all of our x's with 3, whoops, replace all of our x's with 3, okay, oh yeah, this still doesn't work any faster. So if I did that correctly, when I replace all my x values with 3, I should get a value of negative 27. So There's no max value, but we know we have one min value, and the min value is at 3, negative 27. Okay, so that's the kind of information the first derivative gives to you, where the graph is increasing, decreasing, and whether it has a min or max, and if so, where. Okay, then we go on to the second derivative. Yes, this is all still one question. So then I already pre-did the second derivative. So now we make a sign diagram based on that. We set it equal to 0. And then we should see we can factor out a 12x. Whoops. There we go. 12x, x minus 2. And then we make our sign diagram. So we have two critical values, 0 and 2. And this is our sign diagram for the second derivative. Same rules, take any number larger than your largest key point. You know how to do that. So this would be positive. Everything is 2 odd exponents, so it keeps changing. Now, what information does the second derivative give us? This gives us concavity. So in this region, it'll be concave up from minus infinity to 0. It'll be concave down from 0 to 2, and then it'll be concave up from 2 to infinity. Now, inflection points. We have 2 possible inflection points, one at 0 and one at 2. And again, when we run through it, we are replacing it back into the original function. So I think that's on the other screen. So you go back to your original function, replace your x values. Well, where's my original function? You replace all your x values with 0. And that's easy. When x is 0, y is 0. So we have one inflection point at 0, 0. But we also have another one. We also have an inflection point at 2. Again, when you go back to the original function, not the second derivative, and you replace all of your x values with 2. And if I've done that correctly, it should be at negative 16. So we have 2 inflection points, one at 0, 0, and one at 2 minus 16. For today's lesson, we're done. We're not actually graphing or sketching, but we're learning the pieces. But I have Desmosed it to show you what we're building up to next week. So I've already typed it in. So again, we're not sketching today. We're just learning how to use our first, second derivatives, the sign diagrams to get that information. And next week, we're going to have a whole week of just curve sketching. Well, let's see if this matches the information we have. So we have our min value is at, we thought it should have been at 3 and negative 27. Good, we were right. So that is the one min value. You can tell from the graph there's no max value. Now let's look at the concavity. We said that it would be going concave up from minus infinity to 0. It would go concave down from 0 to 3, and then concave up from, oh wait, actually the concavity is here. I don't know if it's going to show. Our inflection point is at 2. I don't know if I can get it exactly. Oh. Okay, I'm going as fast as I can to get this. 2, negative 16. Okay, well, it's somewhere around there. So we see that it'd be concave up, concave down, and then it switches again, concave up. So it's concave up from minus infinity to 0, concave down from 0 to 2, concave up from 2 to infinity. And then if we look at our graph, it says that it would be decreasing from minus infinity to 0, decreasing from 0 to 3, and then increasing 3 to infinity. So everything we saw from the min-max, increasing, decreasing, concavity, inflection points matches. We're not graphing today, but we're just learning the pieces to build up to that next week. Okay, so I know that's a lot of videos to watch through, but like I said, the actual math shouldn't be that hard. And like I said, the more we practice now, easier next week will be. Okay, good luck and have fun with all these terms.